My name is Katie. I work at Google on the web platform team, specifically the scheduling APIs team. And today I'm going to be talking about some work that we did recently involving prioritizing rendering in the Blink scheduler. Okay, so to start off, I want to touch a little bit on why we want to prioritize rendering and why we care, and what exactly that means for the scheduler specifically. So the scheduler decides when we render. It's in charge of picking the time that we run the rendering steps. So it plays a critical role in when we actually put content on the screen. When the DOM is changed, we want to reflect that as fast as possible to the user. That means we want to run the rendering steps pretty quickly. We want the scheduler to choose to run the rendering steps when there's been a change in the DOM. As it turns out, the state of the world previous to these changes was that rendering could be somewhat starved by other work. The scheduler might choose a whole slew of other things that are less important. And especially when we're loading a page, there's a lot of contention on the main thread. A lot of tasks want to run. We might be running timers. We might be doing script. And some of those things are arguably less important than getting content to the screen to the user. And that causes visual lag. So we want to decrease the amount of time it takes to see a DOM update on the screen, because that makes apps seem pretty slow and unresponsive. And even more so, we had real feedback from partners and traces showing that delaying rendering was negatively impacting their metrics and first contentful paint. So a more kind of visual example of this is we're loading, and we've committed our navigation and we have a bunch of script to run and we also want to render to the screen. This is a little bit of a simplification, but this is it. So we're running a bunch of script. After we do the first render, that's our first contentful render, and we see FCP, first contentful paint. And then we run more script, and then we might see another render, and we'll call that largest contentful paint. That's the render that has the most content in the loading process. If we were to prioritize rendering, do it faster after one of these scripts modify the DOM, we could move the first render up a little bit. That gets content to the user faster, and it really improves FCP. So we were seeing traces from partners that had examples of rendering being blocked by a bunch of other tasks. And we decided that this is probably something that we wanted to do something about and something that we could do something about. Okay, so the scheduler chooses when we run the rendering steps. And in order to explain exactly what we did, I'm going to give a very brief overview of the Blink scheduler. This is a pretty big simplification, but it will be just the number of details that we need for the talk. So the Blink scheduler, basically all it does is it manages a bunch of task queues. Each task queue has a priority, so we use prioritized queues. Some of the task queues are specific to certain frames and some of them are global, but that's not super important to this talk. What we're going to talk about is the main thread scheduler. So the render main thread scheduler was what we're going to focus on. And ordering between tasks on the task queue is guaranteed. So when we pick to run tasks, we pick the task queue with the highest priority that has tasks on it to be run, and we run those in order. So it would be the next task that we're going to run, or that the scheduler is going to pick to run, is the highest priority task that is also the oldest task. We do some fancier things. We throttle queues in the background if the render is backgrounded, and we do round robin between tasks posted with and without a delay, but all of that is also not really important to this talk. What is important, though, is that most task queues actually have the same default priority. That is the normal priority. Rendering happens at a normal priority, and so does script and garbage collection and timers and a whole bunch of other stuff. And therein lies the problem. Loading happens at normal priority, a bunch of stuff happens at the same priority, and that's why rendering can be pushed off for so long. So rendering and the scheduler. This will get a little bit more into the relationship of how the scheduler treats rendering. And the answer is not any different than any other task. The rendering steps are also in mainframe. They get queued onto the compositor task queue, which is a normal priority task queue. It is the compositor task queue not because it lives on the compositor thread, it lives on the main thread. It's called that because that's where the tasks that the compositor sends to us go. So the compositor is telling us we need to render, and we put a begin mainframe on the compositor task queue. And then it runs just like any other task. It will be selected as the oldest task on the highest priority queue that has tasks that need to be run. The Blink scheduler doesn't really know what task it's going to run before it runs it. It just, picks a task, or the sequence manager picks a task. So the general flow here is that vsync triggers a begin mainframe. That gets queued on the compositor task queue, and the scheduler will eventually decide to run it when it is the highest priority task that is the oldest. So I'm doing a little visual example because I'm a visual learner and I like pictures. Let's say we have this set of task queues. We have the idle task queue, which is basically where request idle callbacks go to, or other idle work. It runs at a best effort priority. So that's below normal priority. Basically, if we have nothing else to run, then we're going to run things off of the idle task queue. We have the default task queue, which is a smorgasbord of a bunch of different tasks, as is suggested by the name default. It's at the normal priority. The compositor task queue, which I just discussed, runs tasks sent to us from the compositor. And the input task queue, which is a task queue we keep at highest priority because we want to process user input as fast as possible. So all of these tasks are queued by the number. So on the default task queue, we have a couple tasks that were queued first, second, and third, input fourth, idle fifth, and so on. And I'm going to say that each of these tasks is 50 milliseconds. So the first task that we pick is the input task because it's the highest priority. And then the next task is the default task, another default task, another default task, another default task, another default task, and finally we get to rendering, or the compositor task. As you can see, that means that this mainframe, if all of these tasks were 50 milliseconds, winded up waiting 300 milliseconds to go. And that's multiple vsyncs missed and user perceptible delay. And we thought that we could do that sooner. So at this point, you might be thinking, why don't we render whenever the DOM is updated? Why don't we just say, okay, well, we have a begin mainframe, we should just do it immediately? It seems like a great idea, but mainframe can be kind of costly. And if we're doing a lot of frequent slow frames, we can see slowdown on the rest of the page. An example of this is that when we started doing experiments with this, we ran an experiment where we prioritized compositing always. So we put it at a high priority, which essentially kind of meant that we would be rendering whenever the DOM was updated. And we got a complaint that we slowed someone's extension down by 10 seconds because we were running rendering every step of the way. They had a lot of script that was modifying the DOM, chunked up. And so we were trying to render in between each of those scripts. And this caused actual delay. So we want to keep the UI visually responsive by rendering, but we also don't want to impact the rest of the app's latency. So our goal with prioritizing rendering is to improve metrics like FCP, but also not regress metrics like input delay and largest contentful paint. So briefly going back to the loading example that I showed previously, where we moved FCP up by doing the rendering sooner. If we were to always render when we modify the DOM, and each of these scripts modify the DOM, we would get something that looks like this, in which case we're doing a lot of extra rendering. FCP moves up as it did before, but LCP is regressed and moves back because we're rendering too much. So we really want to avoid that, and we had to take that into consideration when we were picking what prioritization scheme we were going to use. Okay, so now I'm going to get into the actual meat and bones of the experiments that we did. So we did 4 different experiments. We implemented 5 different approaches. We did 4 different experiments, and I'll talk a little bit about that. So the first approach I already mentioned is that we wanted to see what would happen if we increased rendering priority just in general. That would be moving the rendering priority from normal to very high. We also did an experiment where we prioritized rendering when we knew it was going to be fast. That way we wouldn't have any long renders that were putting off other work. We did an experiment where we alternated rendering priority. So we would run one task off of the compositor task queue at a normal priority, and then the next task we would run at a high priority. And lastly, we prioritized rendering if we haven't rendered in a while. So if we see that it's been a certain amount of time, we landed on 100 milliseconds, that we haven't seen any rendering happen, we would increase the priority of that task queue and run a task off of that queue, and then decrease the priority once again. And you can kind of think of this like targeting the lower bound on frame rate. We want to be drawing frames every so often. So that's the gist of that. And the last approach which we implemented was prioritizing rendering with a budget, which is rendering gets to be high priority until it exhausts its budget, which could be like CPU time. And then it would be demoted to a normal priority until the budget replenishes. We didn't end up experimenting with this because it's not really clear what the budget for it should be. That's like a really complicated question. We didn't know how fast the budget should even replenish, but there is room to even get more nuanced here than what we ended up with if we decided to continue experimentation. But the TLDR is that we experimented with all of these approaches. We found that the best results were from prioritizing rendering if we haven't rendered in a while. And we landed on that lower bound of frame rate of 10 FPS. Technically, the most gains in metrics that we saw were from always keeping rendering at high priority. But like I discussed earlier, that caused regressions in other metrics. So we settled with this approach. And I will go over how exactly that works. So this is our previous example of task queues with tasks on them. This time the compositor task queue has 2 main frames on it. And we see that we'll run the input task, then we run the default task, and we hit that 100 milliseconds. And we bump the compositor task queue to very high priority. And we run the next task from that task queue because it's now the highest priority queue that has work to do. So instead of waiting 300 milliseconds, this frame only waited 100 milliseconds to run. And now the compositor task queue returns to normal priority, and we keep going as normal. So this experiment saw a 1.5% improvement in navigation to first contentful paint on Android, which is great. We also saw improvements on other platforms in FCP, but Android was the biggest. And this is across the board. So that was really awesome improvement we saw. But there's a little bit more that we could do here to get even more improvements. And that is that not all of the tasks on the compositor task queue are mainframes. So I said earlier, the compositor task queue gets tasks from the compositor to run, and that's not always a rendering task or a task to run the begin mainframe or the rendering steps. So essentially, what we were doing is we were periodically prioritizing a random compositor task, and we didn't know if it was necessarily rendering specifically or just some other task that was on the compositor task queue. So to remedy this, we did an additional experiment. Instead of returning the compositor task queue to normal priority after we run a task, any task, we specifically wait until we see a begin main frame run off of the compositor task queue, and then we return it back to normal priority once we see that frame. So back to the toy example, if we were at our 100 milliseconds with our queue at very high priority and we run a task off of the compositor task queue, but it's not a begin main frame, we leave the compositor task queue at a very high priority, and then we run our main frame. And this time we had to wait 150 milliseconds, but it is a rough target of 10 FPS on a lower bound frame rate. So, and then the compositor task queue returns back to normal priority after we do that frame, and so on. And this experiment saw an additional 1.5% improvement in FCP on Android, which was great. Once again, that in total was about 3% improvement in first contentful paint, navigation to first contentful paint on Android, and also some other platforms to a lesser degree. We also didn't really see any major regressions at all. We didn't regress LCP or input delay or anything like that, which tells us that there is some room to like work even further with this space. We were getting gains without getting regressions means that there's opportunity here to do more optimization, which is really promising. So takeaways, like I just said, there are opportunities in the scheduler to use priorities to make smart decisions. And even more so, we do other things like throttling task queues and stuff like that. But we think that there are more ways that we can take advantage of priorities to help the scheduler choose what to run to make the web faster. And this rendering work that we did, it improved SCP, which is great, but it provides better guarantees around the timing of rendering. We can now say that we will render basically around every 100 milliseconds, and that really helps keep consistency for developers. So yeah, that's it. Any questions? Okay. Have you considered bumping the priority of the compositor task queue if there's an active scroll going on? That may help improve smoothness during UI interaction that is quite sensitive to consistent frame rates. Gosh, I think actually quite the opposite. Scott might have to correct me if I'm wrong here. I think when we're doing a scroll, we actually keep the compositor priority at a low because we don't want to be doing too many expensive renders while we're doing a scroll. And I think the compositor thread actually handles most of the scrolling stuff. So yeah. But we have considered doing different things with the compositor priority based on the lifecycle state. So if a page is loading, we might not want to prioritize compositing too much. But during the rest of the page lifecycle, it might be safer to keep the compositor at a very high priority because we aren't probably doing that much other work. Okay, you mentioned seeing metrics improving for the always prioritizing rendering outside of FCP, however, noted issues during loading. Were there other degradations in post-load scenarios? And could we consider different priorities post-load? Yes, we could definitely consider different priorities post-load. I don't think that we saw any degradation in post-load scenarios on the always prioritized rendering. Mostly, we didn't see any like input delay or scroll gesture regressions. It was mostly regressions in LCP and first input delay. So yeah, one of the things that we are considering is doing or prioritizing queues differently depending on whether or not we're loading.
Katie, I think we did we see smoothness metrics improve?
Yes, we did see
Because
smooth metrics improve.
I think that's one thing that, like, if we were able to do this prioritization post load, like we've kind of talked about, is targeting animations.
Yes, yeah, targeting animations to make animations smoother was one of the things that we were kind of hoping to see post load if we could change or keep the compositor at a high priority. How does this prioritization work with multiple begin mainframes getting composited together? For example, if the viz compositor is waiting on begin mainframes from the renderer and the browser main compositor, but only the renderer compositor is prioritized. And well, hold on, I gotta reread that. I don't know the answer to this question, actually.
So I think this might be from just my not full understanding. Blink, I think, only runs in the renderer, right?
Yes.
But
yes.
Chrome in general has many things producing things to go into the begin frame. So I was trying to understand how this prioritization works across all of Chrome, and how that feeds into it. Like, is the browser main told that its begin frame is now high priority, so it needs to get back, or any of that other stuff? Okay.
Yeah, this just affects the render specifically when the renderer does its portion of the begin mainframe. Yeah, we haven't really, this is all Blink, all render. We haven't really talked about prioritizing compositing in the browser.
Will that ever get, so you haven't gone there, but have you thought about propagating that up to the rest of the browsers so that the browser could at least have some concept of whether a particular begin frame is being prioritized?
No, we haven't talked about that. That could be an interesting idea, actually. Yeah, we were mostly staying in the Blink world, but.
Sounds good. Thank you.
Any changes in the 99th percentile on what? For Android, our FCP improvements were at the 99th percentile, if that is what that question's referring to. Yeah, we saw improvements at all percentiles, so 25th, 50th, 75th, yeah, all of it, which is actually really exciting. Of course, the amount changed, so I think the 99th percentile might have been a little bit smaller than 1.5%, but we did still see improvements there. So that's exciting. Okay, if there are no more questions, I think we are just about at time. So thank you very much for coming to my talk and learning about rendering prioritization today.